welcome to 52nd lecture on network analysis. So, in my last class I told you about some very interesting observations in the form of substitution theorem. Now, today let us do some application of that. In fact, substitution theorem, this replacing this thing is not meant for the circuit analysis, because you have to know the value of I 1 R 1, then only I 1 R 1, but you can represent it like that, and that is the way. KVL equation, mesh equations in this will be same as mesh equations here. Why it will be different? Got the point? That is the idea. Achha, now let us tell you a problem. Suppose you have a network which I will now show like this. Inside this there linear network, linear, always linear networks will be considering. Linear networks, there may be several voltage sources are present, E1, and they are connected, although I am not showing connected, they are connected in very peculiar fashions, E1, E2 dot dot En. There may be number of voltage sources E n. There may be several current sources present in the network I 1, this is I 2 and I n. Apart from this, there may be impedances, all are interconnected, which I am not showing, R, SL, 1 over SC. This way you look at the network 1 by SC, these are all interconnected, which I am not showing in a particular fashion, all of them are interconnected, and this is the network. And to this network, two terminals you have fixed up. You got the idea? That is like this. Suppose you have let me draw it here. You should not have any doubt about this. This is one source, this is another source, there is a current source, all are connected inside. There is resistance, another voltage source, and so on. And two terminals, these two are also connected at some two suitable nodes of this whole network, which are interconnected all these elements in a particular fashion. For a given network, it may look like this. These are the 2 points I am telling A B, and this is the big thing which I have circled it here. There may be inductances, one SL in S domain, you think like that. Achha. Now, across AB is an impedance connected, ZS or Z. I will simply write this S, I will not carry on. In general, it will be ZS, all the voltages are Vs, current sources are Is, like that. Achha, in this network, if I ask you find out the current in this branch Z, through this Z, what is the current flowing? Okay, I will, this inside thing topology is known to me. So, I will calculate this current applying mesh analysis or node analysis, whatever it is, I know I will calculate the current. You will get the answer. Now, what I say, listen carefully. Suppose in this network, same network, if I, so same network, if I say I have changed this impedance to Z plus some delta Z, I have varied this impedance. Earlier it was 5 ohm, I have made it 8 ohm. That means there is a change of 3 ohm. So, this delta Z is not calculus delta Z, it can be anything. With respect to the older value of Z, I have made a change in the value of Z. So, that the total impedance now becomes Z plus delta Z. Suppose in the original network, when Z was connected, the current was I. Same network, same network. linear networks, same network. I have simply varied Z plus delta Z. Then I ask you what will be the new current. Now, one answer could be once again resolve the circuit, find out what is the new current. That is one way of doing it. But we will do it in a slightly different way. I will say, and from onwards you please listen carefully what I am telling. Okay, if you have changed this impedance to Z plus delta Z, this current cannot remain at I, it must have changed to some other value, and that change in current I say it is I plus delta I, where I was the original current, it has changed by some amount, let that changed amount be delta I. This is what I say. Okay. So, my goal is to find out the new current when Z has been changed to Z plus delta Z. These 2 points A B are same, this network is same, where there may be several sources connected. Therefore, solving the circuit once again may look tedious. What is the point with all sources considered, simply because you have changed impedance in some branch of this network? I have to go through all this ordeal to find out this new current. Now, there may be another way of thinking to attack this problem. It is like this. Okay, the voltage across AB when the impedance is Z plus delta Z, first see what is this? It is Z plus delta Z into I plus delta I. These are all S in terms of, you can think, general impedance Z. Now, this can be written as Z plus delta Z into I plus Z plus delta Z into del I. This way I can write, is not one impedance into I plus this thing, and this one I can write it as I into Z plus I into delta Z plus Z into delta, this you do not break, leave it as it is, plus Z plus delta Z into delta I. Like this I can write this whole voltage drop across AB when the impedance is like this, I can write it, is not. Now, what I will do is this I Z plus this term I into delta Z and delta Z into delta I, this term I can write it as I plus delta I into delta Z and then plus Z into delta I. Correct? These 4 terms are this way I will write it. Okay. Achha, now see these interesting arguments. Okay, here between these 2 points A and B, A and B, across this A and B only I am drawing, here that network is connected. Here I can look at it some voltage source, this drop I will treat it as a this current is I plus delta I, mind you, in this network. From this network only I am drawing. It then I am telling that here is a battery of magnitude I z. Do I know this value? Yes, you have given me the value of I and z. Earlier I have told you in the statement of the problem, I know the value of I when z is connected. So, I can replace that impedance by a voltage source with the help of substitution theorem, that is what I will do. So, there is a source like this. Then I will say there is another source I plus delta I. Here is an impedance I into delta z. This term is I z is there plus I into delta z. Achha, about this term I into delta z, it is also known, because I was the original current when z was connected, it was given to me, and delta z by which amount z has been changed, that is also known to me. So, this is known. Therefore, I z and all these remaining terms, I can write it as another voltage source I into delta z. I can write it I into delta z plus another term is there, is not? What is that term? Got the point? I z, then I plus delta I into delta z. So, I into delta z will be there. Okay, first I will do like this. There is a voltage drop, I will write it as that is what you should do is this I will write it as I plus delta I into delta z and plus another voltage source I will write z into delta I. This way I can write it with the help of substitution theorem. I may think these voltage drops are nothing but batteries, but polarities are important like this, no problem. 3 voltage sources are connected in series in this fashion. And what is between A and B? It is this network, this same network. See, the arguments are so interesting. It is like this. Achha, now I know superposition theorem. Okay? I will say, look, in this equation, how many sources are there? Okay, all the internal sources that present in the network inside, several voltage current sources are there. Those sources present and I z only I will apply superposition to these sources. So, let me redraw here so that you do not miss the point. So, what I am planning to do, inside the networks let all the sources be present, do not disturb that impedances sources. This is A, this is B. What I am telling, here these 3 sources are present, of which I will tell only I z is present. Whatever will be the current, that I will note down. Then I will consider this source is only present, other sources replaced by short circuit, this shorted, and all the internal sources of the network and this I z present. What will be the current here? This circuit is the original circuit, all the internal sources present, Z is present. So, this current is I, it is already known. Then what I will tell, I will draw here only, let it be slightly clumsy, so that we understand what we are doing. So, with all internal sources and I z present, this current has to be I, because this is what we started with. This network and this network is same, because I z can be replaced by Z, because the current is I. That is what we learned from the substitution theorem. Okay. Then I will say only these two sources are present and this is shorted. So, this I will short and these two sources are present. What are these two sources? One is this source, that is I plus delta I, into delta Z, and then Z delta I, Z delta I. These two sources are present, suppose I say. Are you with me? I mean, absolutely. What I have done so far? I have done that this was the given networks, Z is the current, I is the current. Problem statement is very simple. I simply change Z to Z plus delta Z. I want to find out the new current. New current, I assume it to be that old current plus that changed component I plus delta Y. Then what will be the voltage drop in this network? This Z into this I. This can be expanded in this way. Then I say that okay, there are now these three sources. So, this I z can be replaced by a voltage drop battery with I z magnitude, with this polarity. Why this polarity? I was entering like that. Similarly, I plus delta I z and Z plus delta I. Now, what I am telling, all these sources are present and I z is present, these two sources are absent, you get this network, and this network is same as this network. So, this current is I. Then all these sources are present here, networks, sources present, then this to this. This fellow is absent, I have taken this into account, and other two sources are present. No, all internal sources present and operator, and then all the sources. Now the thing is, these two sources will be, yes, you are right. This now I am applying superposition. So, I will tell that these two sources are present and all internal sources should be replaced by their internal impedances, correct, absolutely. And current sources open, voltage sources shorted. So, this will be the network now. Now, then I will say this network, in this network delta I must be present. These sources alone present with internal sources replaced by their internal impedances must have produced delta I. That is why when this and all the networks are present, it should be I plus delta I. So, who is the contributor for this delta I? It is these two sources, it looks like. Clear? Acha. Now, this I will slightly, this quantity I plus delta I into delta Z, that is this one, plus Z delta I, This is the whole thing, whole voltage drop here. Now, this can be written as is equal to delta I into Z plus delta Z plus I into delta Z. These two things can be written like this, is not? Therefore, I will say that here this thing can be also replaced by these two things. One is I into delta Z plus delta I into Z plus delta Z. Crucial step. These two are same as this network, nothing changes. Current is delta I, there is a battery here delta I into Z plus delta Z. Therefore, I will say that this network, after this I am proceeding here, this is the network. All internal sources replaced by their internal impedances, replaced by internal impedances, and these are the 2 points A and B, where this current is delta I and this drop is delta I into Z plus delta Z. Therefore, I can represent it by some impedance Z plus delta Z, Z plus delta Z, because this is the drop between these 2 points delta I into Z plus delta Z, and then a source of voltage whose magnitude is I into delta Z, and we are done. Got the point. Therefore, I will say that okay, one option is connect new impedance Z plus delta Z, resolve the network with all sources of the network present with this impedance Z plus delta Z. You can solve for this current the same way you did when only Z was present. That is straight cut solution, no problem. But we were looking at some different way whether it can be solved. What did I do? There are how many sources present? All internal sources are present, there is no source here. But when you change this impedance to Z plus delta Z, the voltage drop between A and B should be this current into this impedance. Now, this can be expanded in the way like that. Therefore, I can represent it as 3 batteries, 3 voltage sources, one with IZ, another with I plus delta I into delta Z, and so on. So, this is IZ, I plus delta I delta Z, and this one you do not write. This one I have done like this, I can do it like this IZ. After doing this, I am saying when all the internal sources of the network present and this voltage source is present, this will be the network. What is that network? All internal sources present and only this source is present. Then what should be the current? From this I know it must be I, it was known current is I. Then I will say current in this network will be when this is replaced by a short circuit. All these sources are replaced by their internal impedances. Then this current must have been contributed by this term and this term, because this can be manipulated as I z, I z I have taken into account I into delta z is there, I into delta z this term, and then delta z plus this thing will give you delta I into z plus delta z. So, with these two sources present, and these sources must contribute delta I, that is why the superposition theorem is. And then this delta I will calculate, and I will add to this original current, and then say that when z plus delta z you have connected current is I plus delta I. Let us take a simple example. What I mean by this? That is, in other words, what I am telling, once again final result is this A B was there was Z, this current was I, there were several sources present, several elements are present, all are connected, things like that. This was I. Now, my problem is all network should be present once again same as it is. All the sources, internal sources are present. These are A B, these are A B, and I will change this impedance to Z plus delta Z. And I am interested to know what is this new current, New current I told let me call it I plus delta I, that old current I plus that change. Then I am telling to find out that current, here is an option, take the network, replace the sources by internal impedances. You will have A B here. Then connect this impedance Z plus delta Z, which is known by what amount I have done, and here you replace it by a voltage source whose value is I into delta Z. So, in this network it is expected necessary steps will be less, because no sources are present here, absent of any sources, and this quantity is it known? Yes, the old current was I into by what amount you have changed this Z, I delta Z with correct polarity. Z plus del Z is known, yes. So, I will solve this network with only one source, that is the advantage. And what current you will get? Delta I. And after you get delta I, then you say the actual current through Z plus delta Z in this network, when all the sources are present, this fellow is present and this fellow, that will be equal to I plus delta I you do. So, target is to calculate this delta I. Take a numerical example to calculate this. Suppose you have, I will take a very simple example. Suppose you have a network, that previous network only, let me say 4 ohm, this is 5 ohm, 1 ohm, and this is 5 ohm. here is only one source. That was 30 volt, 30 volt. And we have already solved this circuit. This is 0.6 ohm. The currents were known to be 10 ampere here, and this was 4 ampere, and this was 6 ampere. We know this. Therefore, this suppose these are my A B points, A and B points are there, and this current was known to be 4 ampere. So, here I was 4 ampere and your Z was 5 ohm, like that. Now, I say that this Z has been increased by, let, so Z was 5 ohm, let 5 ohm impedance is changed to 8 ohm. Then I will say delta Z is equal to 3 ohm, is not? I into delta Z is how much? I can calculate, this will be 12 volt, 3 into 4, because this current was known. Then I am telling with this impedance changed to 8 ohm, delta Z 3 ohm, you redraw the circuit with these are the sources present in the network, this source replaced by short circuit 0.6 ohm, let this be 4 ohm, we have not done anything with them, and this will be 4 ohm, no change here. This was my A, this was my B, and there you this was 1 ohm, sorry, this was 1 ohm. This is my AB, and there you connect a voltage source plus minus 12 volt, I into delta Z, and this impedance you show only 3 ohm, is not? Z plus delta Z, correct, Z plus delta Z is equal to 8 ohm. Now, solve for this current delta I. Can it be easily solved? Difficult. Anyway, now in this network what I am trying to point out is, it is a very simple circuit with single source. So, calculate this current you calculate delta I. If possible you can tell, otherwise I will leave it to you, calculate delta I in this direction, let it come positive, negative, I do not mind, it might come negative in this case. So, after you calculate delta I, then add to this initial current 4 ohm to get the new current in this minus 1.26 ampere delta. So, it will be 4 minus 1.26 ampere. If you calculate this current, how much it is? 2.74 ampere. Now, you should cross check with this new value, that is 8 ohm and 1 ohm in parallel, and it should come same. See, the idea is that you need not consider once again resolve the circuit in its totality. You replace only one source I into delta Z, this impedance Z plus delta Z, and solve for the current which will give you delta I. So, it will come same, I leave it as an exercise, that is with this replaced by 8 ohm, solve this network, get this current, and then solve this network with 5 ohm, it was already known. So, it is a nice way of thinking this. Suppose a big network is there, very big network, only one branch impedance I change, then better try to solve for delta I, then add to the previous current, it is suppose solved once and get the answer. Thank you.